Hello, today we will discuss Fermat's little theorem, which tells us that if we are given any positive integer a to the p power equals a mod p. We will discuss two different solutions, and the first one will be about induction on a. For a equals 1, it is clear that a to the p equals a mod p. And let's assume that this is correct for every number before n, and we know that n to the p equals n mod p, and try to show this for n plus 1. n plus 1 to the p must be equal n plus 1 mod p. To show this, we need to use the fact that p choose k is always divisible by p. p choose k, this number equals p factorial over k factorial times p minus k factorial. And if you look at the numerator, this number is always divisible by p because we have p in the numerator and we don't have any multiple of p in the denominator. So this number always is divisible by p. Now we can use binomial expansion of this n plus 1 to the p power, and we will get that n to the p plus p choose 1 times n to the p minus 1 plus p choose 2 times n to the p minus 2, and last terms will be p choose p minus 1 times n plus 1. And if we look at all these terms are divisible by p because of this lemma, so this must be equal n to the p plus 1 mod p. But we know that n to the p is already equal n, so this equals n plus 1 mod p. So we have proved that n plus 1 to the p power equals n plus 1 mod p for every prime number p. So we have proved Fermat's little theorem, but now I want to discuss second solution about the Fermat's little theorem. And in this case, we need to use the fact that a to the p minus 1 will be always equal 1 mod p. This is mostly used representation of Fermat's theorem because a to the p equals a mod p. This is similar that a times a to the p minus 1 is divisible by p. So if a is multiple of p, it's clear that a to the p power equals a mod p. And now discuss the case, then a is coprime to p. And now look at numbers. A, 2 times a, 3 times a, up to p minus 1 times a. Now we will prove that all these numbers will give us different remainders mod p. And contradiction of this is that I times a equals j times a mod p. If we take a out of brackets, we will get that a times I minus j equals 0 mod p. If we use the fact that a is coprime to p, then we get that I minus j is equal 0 mod p. And clearly this is impossible because both of these numbers are less than p. So all these numbers must be a permutation of numbers from 1 to p minus 1. So if we take the product of these numbers, must be equal product of these numbers mod p. And now look at what will be product of the first left hand side. That would be a to the p minus 1, a to the p minus 1 power times p minus 1 factorial. And this number must be equal p minus 1 factorial mod p, because this is right hand side and this is left hand side. We know that p minus 1 factorial is not divisible by p, so we can erase this number and we will get that a to the p minus 1 equals 1 mod p, And this was what we wanted to show. So if you got any remarks or theorems if you want to discuss, please write in the comments.